I want to talk about piecewise defined functions and function composition. A piecewise defined function is one where it's defined differently depending on the domain. I always like to kind of look at where the big benchmark x values are. This function starts at -1. It's not even defined on the other side of -1. And it changes. You see it's from -1 to 1, then a different function at 1, then a different function on the right side of 1. So I kind of like to really pay attention to that, and sometimes maybe even make a note that 1 is important, that there's something happening along the x value of 1. So first of all, the function is -x plus 1. So I know it has a y-intercept of 1, like that, and a slope of -1. So something like this. Now, if you recall from previous courses how we denote the difference between a spot where it could be equal and where it can't, where it could be equal we put a closed circle, and where it's just less than or greater than we put a open circle. So I'm going to do that. We're going to put a closed circle here where it starts and an open circle here. Okay. And I may just really quickly erase some of this. Next, at 1, the function just takes on a value of 2. So for that one spot, we just take on a value of 2 like that. Closed circle. And past that, we take on a value of x squared. So x squared, a lot of times this part is the hardest because it doesn't start at 0. So I'm going to just plug in 1 to the function. 1 squared is 1. Getting a little bit tight in there. If you think about 2 squared, that's 4. Maybe just put that point up here. So it's going to look like the parabola. It's very steep. So we have the linear function, -x plus 1, from -1 to 0, closed circle here because it could be equal, open here because it can't. The function takes on the value 2 at x equals 1, so at x equals 1 we have y equals 2, and past 1 we take on the function x squared. So looking at this function and its domain, we can really get the domain just by looking up here at where it's defined. But you could also look here and say, well, it starts at -1 and it's defined all the way to the right of that. So our domain is from -1 to infinity. For range, remember that's y values. You see it never goes below this axis. It's defined everywhere up, but it never goes below the axis. And in fact, because of that open circle, it's not even defined at the axis, so we go from 0 to infinity. Another thing you may be asked to do is come up with a function given a graph. Now, I start usually by listing the domain. You'll see we take on one function from -infinity to -1. We take on a different function from -1 to 0. And we take on a different function from 0 on. So I'm going to write that down. When x is less than -1, and notice it's got to be less than because of that open circle, we take on a different function when we're going from -1 to 0. And again, I said equal because we have closed circles, so it could be equal. And we take on a different function when we're just greater than 0. Okay. Now I go back and actually find the functions. Well, the first one actually isn't too bad because, of course, it's just a horizontal line at y equals 3. So I'm just going to say, oh, it's 3. This next function is a linear function. It's got a slope of -2. And nice, I can actually see the y-intercept. It's just going to be -2x. If it were harder, I would certainly recommend maybe using point slope form. Let's say you didn't have the y-intercept. You said, well, I see the slope is -2 and it goes through the point -1, 2. And you could do something like that and then put that in there, and that would be really nice. Okay. And our final equation, it looks like we've got a slope of 1/4, and again I see the y-intercept is -2, so I could just put 1/4 x minus 2. But if it was a little harder to see, use your point slope form. You could easily do 1/4. Maybe we would want to use that point, maybe do x minus 4 minus 1 or something like that, and you're going to get the exact same answer. So don't feel like you have to use the y-intercept. Sometimes it's easier not to. Finally, function composition was the last thing we covered today. Remember that this is the symbol for function composition. It means f composed with g. It simply means we do g first and plug that answer into f. So let's do that. Let's plug in 4 to g. So 6 multiplied by 4 squared, so 6 multiplied by 16 is 96. So that means we are actually doing f of 96. So 3 multiplied by 96 minus 4. So 288 minus 4 is 284. The next question asks us to just put the entire function g into f. You see, instead of a number, that was pretty easy. We just plugged in 4 to g, got an answer, and plugged the answer into f. Now we're just going to take the whole function and put that into f. So we'll do something like this. We'll take g and we'll put it into f. Just like that. So you'll see that g, the function g, has now been put inside of f. We just replaced x with g. The other way, putting f into g, just as simple. Place the x with g. Now, clearly you could do some simplifying here. You could say, well, this is just 18x squared minus 4, but I wanted to kind of leave it to make sure you saw that how the composition had taken place.